Time to get started. Welcome back, everybody. I hope you had a good little break. And I hope you noticed I posted the homework assignment this morning. Sorry about that. I meant to post it, last week sometime, but I messed it up. So there will be homework due tomorrow. Check it out. It's not a very long assignment. If for some reason my lateness has screwed up your week or something like that, please let me know. We can talk about it. I hope that that's not an inconvenience to anybody. All right, so we are talking about graph theory. I also wanted to say, sorry, my recording of the class last time didn't work out. So if you weren't here, you probably didn't get the whole deal. But what can I say? My pencil ran out of battery power, so it was great. I did the markers the old-fashioned way. Anyway, we're talking about graph theory, and last time we did not talk about very much that was complicated at all. Just the basics of what graph theory is all about. A graph is, a bunch of points called vertices, which are connected to one another by edges. And what I want to talk about today is kind of the next thing on the list as far as the topics about graph theory, and that is something called Euler circuits. This first word there, Euler, is a person's name. It's pronounced Euler. That's why I said Euler. You may be tempted to say Euler. You sound foolish if you say Euler. Don't say Euler. Say Euler. It's a German name, and in German you say Oi when it's EU. Euler. All right. This so we're talking about Euler circuits in a graph. This is a particular type of thing that you can do with graphs, which is an interesting thing. Actually, this was in many ways the OG graph theory problem. Graph theory, in terms of the history of mathematics, is a fairly recent thing. Maybe like the 1700s is when it was sort of invented, but it became really popular really only in the 20th century. But Euler was a person, and Euler was responsible for inventing many things, but one of them is basically what we now consider to be graph theory, was pretty much invented by Euler. But anyway, the original graph theory problem, which Euler wrote about, is sort of a famous math problem called the 7 bridges of Königsberg, which is a city somewhere in Europe. The 7 bridges, and this is a real place, which at some point in history really had 7 bridges, although I believe now the bridges have been reconfigured since then, so you can't exactly go there. But here's the idea. There's a river in the city of Königsberg, and the river has 2 islands in it, like this, but all this is water, all right? So it has 2 islands and sort of the land on the top and the land on the bottom. This is a river. And there are bridges going from one place to another, and there were 7 of them. There's one here, there's a bridge here, there's a bridge here. Actually, there's 2 bridges on each of those. There's one going across the middle, and then one here and one here. Those are the 7 bridges of Königsberg. All right, and I believe Euler lived in this city, or went there at least. And heard about the local people used to talk about the bridges. And there was a question that everybody used to like to chat about, and that is, can you walk across each bridge once? One time, no repeats, and end up back where you started. This is the 7 bridges problem, all right? And this one problem sort of led to the birth of graph theory. I think one obstacle here is that it doesn't really sound like a mathematical question. Although, if you think about it, I think you probably will eventually agree that this is somehow a little puzzle, a little sort of logic puzzle that you could in some way use math to solve. But can you walk across each bridge one time without any repeats? That's the question?
Would be one time just there or there and back?
One time is just there. Yeah, there and back would be a repeat. So that's not allowed. Yeah. Just by looking, do you have an answer?
Question.
Yeah.
Would you, so for like the two, like, so there's the river, there's like two like little islands, and then the land masses.
Yeah.
Could you walk across the land masses and that not counting as like repeating a place, or would you just have to only touch down once?
Yeah, it's only the bridges that cannot be repeated. So you can walk around, you can like walk back and forth down here. Is that what you mean? Yeah. You think you can?
Yeah.
Can you tell me how? I will follow with my finger. How about starting down here?
You can start right in front of the second island with the three bridges connecting.
Okay.
So start there, walk up, wait, never mind, hold on. Never mind.
The answer is no, you can't do it.
Oh, you can?
Yeah, maybe I should have said that before I asked you to show me how to do it. Yeah. It turns out this is impossible. And if you just try, like with your finger, to do it, probably you can try for a few minutes, and then you'll be like, all right, this you probably can't do this. The real problem, though, like the real math problem, is to actually explain why can't you do it? Why is it really impossible? Versus I just couldn't figure out how to do it. There's a big difference between I can't do it versus it's actually impossible. All right. So the question here: can you walk across each bridge one time? The answer is actually no, you can't do it. And Euler was the first person to actually demonstrate why it's impossible, beyond just saying, like, I can't figure out how to do it. So the answer here is no. How did Euler end up demonstrating this? Basically, he invented graph theory and then figured this out using graph theory. So this is a big accomplishment. I think at the time it was not really regarded as very important, because what was important in math back then was like calculus. And of course, calculus is still important now. But nowadays, graph theory is very important in the world, the real world. And so now we recognize this as a big achievement, although at the time it probably didn't sound like anything. How is this related at all to graph theory? So you might, just looking at the problem, if you are trying to do this mathematically, somehow relate this to math in some way, you would be tempted to say this is like a geometry problem, because it's like a picture here and it's got shapes on it, I guess. Although almost nothing that is traditionally geometric about this is relevant at all. For instance, the two islands are like oval shapes. Is that actually important here? No, it's not. It doesn't matter what shape these are. The bridges are kind of straight lines, but also that doesn't matter. The land masses are also sort of, I drew this one as straight. This one has a little curve to it. Does that really matter? None of that matters, even though if this was a real geometry problem, it would matter if things were curved or straight. That's important in geometry, but not important at all here. So what's Euler's, I think Euler's big sort of stroke of genius here is to realize that almost nothing about this picture is important. There are important things about this, but it has nothing to do with what we would traditionally call geometry. So can I just say this is not a geometry problem? And this is why this was so hard to do at the time. I'm talking about like late 1700s, I believe, is when Euler was working. This was hard to handle at the time just because it looks like geometry, but it's not. And it's something else which had not been invented yet. This is not a geometry problem, all right? Really, it's a graph theory problem. It's a graph theory problem which didn't exist at the time. Graph theory problem. All right. What about this is actually important? I would say the only thing that's important about the diagram is where are the land masses and how are they connected by bridges. So I would say, if I were looking at this diagram, I would say there's a thing over here, there's a thing over here. There's also a thing up here and a thing down here. But it doesn't, nothing about the shapes of those things or anything matters, right? It's just that there's a thing, there's an island over here and another one over there, and then there's also a land on the top, and there's also a land on the bottom. And there are bridges which connect them up in certain ways. There is a bridge going across the middle. This is in red is my like translation into a graph. There is a bridge going across the middle. There's also a bridge from the right one up to the top. There's also a bridge from the right one down to the bottom. There's 2 bridges here and 2 bridges here, all right? So what you see in red, that's the only important business about this problem. Nothing else in the picture matters. So this whole thing here, it's a graph theory problem, and it's really about this graph specifically, a graph with 4 vertices that are connected in this particular way. All right? That's really what the bridges problem is about. And then to ask the question that was originally asked in the bridges problem is, can I walk across every bridge once without repeating any and end up back where I started? Translated that into the language of the graph, it would say, is there a circuit? Remember, this is a word that we had last time. A circuit means a path through the graph which ends up at the same place where it started. So is there a circuit which uses every edge once? One time. By which I mean no repeats. All right? This is the graph theory version of that bridges problem. I've translated it just purely into an abstract question about this graph. All right? And there's a name for that. A circuit which uses every edge one time with no repeats, that is called an Euler circuit, which we named it after him because he came up with the idea of this whole thing. So I'll write that as the definition here. A circuit in a graph, remember a circuit is just a path which begins and ends at the same place. A circuit which uses each edge exactly once. That means no more, no less than once. One time with no repeats. A circuit which uses each edge exactly once is called an Euler circuit. Don't say Euler. You sound foolish. I will correct you if you say Euler. I'm not big on correcting people in general in my personal life, but I will correct a fool who says Euler. All right? This is called an Euler circuit. So the big question for today is, how do you know, if you're looking at a graph, how do you know if it has an Euler circuit or not? And furthermore, if you decide it does have one, can you actually sort of draw it in there? So the big question is how to tell / find if there is an Euler circuit. This is a typical, homework or test question. I give you a graph. You tell me, is there an Euler circuit or not? And if your answer is yes, then can you actually show me how to do it? Show me where it is. All right? This is the big question. It's not an easy question, just because it's a complicated thing here. You could, I hope that you did this sort of in your head a little bit. You could just sort of try to walk around here and see if you really can use every edge once without any repeats. You should eventually convince yourself, yeah, that's probably not possible. But it's not at all easy to be, sort of well and truly convinced logically that it really is logically impossible. All right, let's try some simple examples where it is possible. I mean, if it is possible, usually you can just sort of stare at it long enough and figure it out. How about this graph right here, like so, with a vertex in the middle there, and of course a vertex at each crossing over here, and then I'm going to put some extra edges like that. All right, does this one have an Euler circuit or not? The answer is yes, this one actually does. I made this example so that it would. If I were to, so this one has an Euler circuit. This one has an Euler circuit. What that means, remember, is it is possible to make a circuit that goes around the whole graph, uses every edge once without repeating any, and then ends up back where it started. You want to see if I can do this? I know what I'm doing here, so I'm pretty confident in myself. I'm going to start in the corner up there, and check it out. I'm going to draw where you would go. I'm just like imagining I'm a little guy walking around on here. I'm going to try to do this without ever using the same edge twice. I hope you are impressed. There you go. I did it. I covered every edge without using any edge more than once. All right? If that impressed you, by the end of today, you will be able to perform similar amazing feats. This is not really that hard. You have to know what to look for when you're looking at a graph like this. But this has an Euler circuit. There it is. All right? How can you tell if there is or is not one? And then how could I, be sure that there isn't one? How about this? This graph right here. This one actually has no Euler circuit. Although I would say it's not exactly obvious why not. I mean, you can, like I said before, the best you can do is say like, well, I tried and I wasn't able to make it happen. But it's hard to say exactly why not. You could try, I suppose, start up here, maybe go down here, maybe come back around there, maybe go up here, down here. I think I'm going to get stuck. If I go like that now, I have nowhere else to go from the middle because I'm not allowed to reuse either of those edges, right? So this has no Euler circuit. I mean, I just tried and failed, but like I said, that doesn't mean that it's impossible. It just means that I messed it up. Can I just say, hard to say exactly why not. Any comments or questions so far? Do you think you can say exactly why not? I don't think it's obvious. Exactly why not. Turns out, though, Euler figured all of this out, and this is something that, in my opinion, is somewhat of a beautiful fact, a beautiful mathematical fact. It turns out, actually, it's actually very easy to tell. Once I tell you the secret, you will be able to immediately tell me if a graph has an Euler circuit or not. It's actually very easy to tell if a Euler circuit exists or not. You just have to know the trick. And Euler figured this out. This is what, I will just tell you first, and then we'll talk a little bit about it. This is a theorem. This is like Euler's theorem about Euler circuits. Euler did a lot of stuff, and there's actually many things that are called Euler's theorem. This one is sometimes, well, it doesn't really have its own name. I would call it Euler's theorem about Euler circuits. It says that a graph has an Euler circuit. I'm going to tell you when. Here's a fancy mathematical phrase here. If and only if. I will say in a moment what I mean by that. A graph has an Euler circuit if and only if all vertices have even degree. This turns out to be about the degree. A graph has an Euler circuit if and only if all vertices have even degree. This phrase, if and only if here, it means those two things are logically the same. So when it has an Euler circuit, that means that all the vertices have to be even degree. And the other way around is true. If all the vertices have even degree, then automatically it has an Euler circuit. The graph has an Euler circuit if and only if all vertices have even degree. This if and only if means that these two statements, like this and this, they are logically equivalent. Logically the same. All right. What I said that this is kind of a mathematically beautiful fact. What I mean by that, I don't know if you are an appreciator of mathematical beauty. what I mean by that is one thing that we recognize as beautiful in mathematics is when something on its surface sounds like a complicated idea, but we realize actually it's much simpler than we thought it was. And this, I think, is an example of that. The concept of whether a graph has an Euler circuit or not is not at all easy to tell. It's not obvious when you're looking at a graph. But if you know this fact, actually this is very easy to tell if all vertices have even degree or not. I hope you remember the degree is just the number of edges that touch each vertex. And you can easily just look and see if they're all even or not. Like, would you mind if I scroll up to my examples here? What are the degrees of these graphs? I mean, of these vertices? You look at each vertex. Remember, the degree is how many edges touch it. Here, I'll just draw that one again, since I encumbered it a little. The degree is how many edges touch each vertex. We could draw in the degrees here. Can anybody say, what's the degree of this one up here? How many edges are touching that one? 4. Yeah, this, if you know what you're looking for, this is not hard to do. That one is the degree 4. How about over here? You count. 1, 2, 3, 4. There are 4 edges that touch this vertex. So that one's also a 4. Actually, I think they're all 4 on this picture. The one in the middle is a 4. This one down here is a 4. I put an extra little guy there. That wasn't supposed to be there. And that's a 4. All right? When I ask you, is there an Euler circuit or not? That's the same as asking, are they all even? And are they all even? Yes, they are. That means there is an Euler circuit. So here, these are all even. So there is an Euler circuit. All right? Now the question of actually, can you draw it? That's a separate question. But the question of is there or is there not an Euler circuit is very easy to answer by looking at the degrees. What about that other example that I drew? Now we will be able to see. What are the degrees here? Can anybody say what's the degree of the one on the top? Show me the fingers. They're showing me 3. Yeah, the degree on top is 3. And actually they're all 3 in this example, right? So these are not all even. So there is no Euler circuit. This is Euler's theorem about Euler circuits. It tells you whether or not there is an Euler circuit. All it involves is looking at the degrees. Are they all even or not? Now, in this case, they were either all even or all odd. Sometimes there can be a mixture. There can be some evens and some odds. The rule is if they're all even, it has an Euler circuit. If there's any odds, it does not have an Euler circuit. All right. Can we talk briefly about? Yeah. Can we talk? So one thing I want to say. Sorry. What happened? Done. Oh, I just made a screenshot. Okay. Yes, can I say one thing about Euler's theorem? It tells you if there is an Euler circuit or not. It doesn't actually tell you where it is, how to draw it. Like what I did before, I was drawing it in there. The Euler's theorem doesn't tell you that. So the theorem tells if an Euler circuit exists or not. Circuit. It does not say like where it is. All right, so that's a separate thing that we need to talk about. But the theorem tells you if an Euler circuit exists or not. This is called an existence theorem. And mathematicians like existence theorems. Some people think that existence theorems are kind of silly. You want to hear a hilarious math joke about existence theorems? This is going to be awesome. You ready for this? This is one of those jokes where there's like 3 different people in the same somewhat ordinary situation, and the first 2 people behave in an ordinary way, and the third person behaves in a silly way, and that's why it's funny. You know what I'm talking about? This is the mathematical structure of the joke first. So the joke is there's let's say a chemist and a physicist and a mathematician staying in a hotel. They're in their own rooms, and in the middle of the night, they go to sleep. This joke is going to be hilarious. You'll be sad that you left the room. Watch it on YouTube. She did. In the middle of the night, the chemist wakes up in the hotel bed and realizes that like the bottom of the bed is on fire. And the chemist looks around the room and sees they have like the ice bucket from the night before sitting next to the bed. So they take the ice bucket, dump it on the fire. Fire goes out. Everything's fine. They go back to sleep. And then the physicist in the same situation wakes up, sees that the bed is on fire. The physicist gets there's a pile of blankets on the floor that they didn't need. They get the pile of blankets together and smother the fire. The fire goes out. Everything's fine. The physicist goes back to sleep. All right. The mathematician wakes up in the middle of the night. This is the funny part. You ready for this? The mathematician wakes up. The bottom of the bed is on fire. The mathematician looks at the ice bucket. He's like, okay. Sees the pile of blankets on the floor. He's like, okay, a solution exists. And then goes back to sleep. You get it? Yeah. A solution. So this is a joke about existence theorems. There are some mathematical facts. They only tell you if a solution exists. They don't actually tell you how to do it or how to find it or something like that. And that's what this is like, the Euler circuit, the theorem about the Euler circuits. All right? Yes?
What if, for example, like in the last examples, the numbers were all the same, like 4, 4, 4, 4, 3, 3, 4. Could be there, for example, that 1 is 3, 1 is 4. And what would it say then?
Yeah, so if they are all even, that's when there's an Euler circuit. If there's any odds, then there's no Euler circuit. So it can sometimes be a mixture of evens and odds. We're going to do a lot of examples where we'll see that. Can we talk just briefly about why this is true? It is actually important to understand a little bit about what does it have to do with degree being even. So why does Euler circuit make all the degrees even? Actually, it's not so hard to think this through and realize that if there is an Euler circuit, then all the degrees have to be even. Think about if I imagine in my graph somewhere, let's just say there's a vertex somewhere, right? And I have maybe several edges coming off. This Euler circuit in the graph, remember I drew it like with a red line before. The Euler circuit, it must visit each vertex, right? Because it has to cover all the edges. So actually, it's going to visit each vertex several times. It has to visit each vertex. Maybe it comes in this way and comes back out that way. All right. Must visit each vertex probably several times. You missed the hilarious joke. It was awesome. Ask your friends. You'll probably see it when it goes viral on the YouTube. The Euler circuit, if it exists, it has to visit each vertex probably several times. It comes in along one edge and it goes back out along some other edge. All right? And then later on, it's going to come back here along one edge and come back out along some other edge. So maybe it does that, and then over here it goes around somewhere else, right? Eventually, it comes back along here and back out through here, does some more stuff. All right? My claim is that if this is really going to work out, the degree here actually has to be even. Anybody have a feeling like that? Actually, it can't work in this picture that I drew here because there's an odd number. I think there's 1, 2, 3, 4, 5, 6, 7. Yeah, there's an odd number here, so this actually is not going to work here. But anybody have an idea? It has to, yeah?
Like if you start outside or inside, it doesn't matter. You need an even number to get there at the point where you started. And if it's uneven, you never get there where you started.
Yeah, it has to be an even number. I think if I were to try to explain this, it would have to something to do with the number of times the red line has to arrive and then leave again, right? Do you have some?
Yeah, if it's an even number, it means it can be divided up into groups. So they
Yep.
can pass over the vertices as many times as they need to, but if it's an even number, that means it can pass over like an equal, sort of an equal amount of times. Does that make sense?
Yes, these are even, which means this red line, it can arrive and then leave again, and then arrive and then leave again. It has to have some number where it comes in, and then some number where it goes back out. And actually, this red line is not allowed to arrive and then not leave afterwards, because it has to be a circuit, which means it has to end up eventually back where it started. This line here has to, it's like it comes in this way and then it goes back out. Now, in this picture, it comes in there and then it's going to get stuck. Right? Because that's because this is an odd number of edges. It has to arrive the same amount of times that it leaves, right? Always want to come, but they never want to leave, as she says. In this picture, you get stuck because there's an extra edge here, and then you got no other edge to use to get back out of here and finish the circuit, all right? That's the problem with the odd. So I'm going to say something like this. The Euler circuit must visit each vertex, probably several times, and the circuit needs an edge to arrive on plus an edge to depart on. All right? And each little arrival plus a departure requires 2 edges. You got to do this 2 edges at a time. And if you ever had an extra edge left over, you're going to get stuck. It's going to arrive along that edge, but it won't be able to depart again. All right? So the circuit needs an edge to arrive on plus an edge to depart on. I'm going to say this requires all of the edges to come in groups of 2. And that means there has to be an even number of them. That's the connection between the Euler circuit existing and this kind of evens and odds business. All right. So this requires all the edges to come in groups of 2. I mean all the edges that are touching this vertex right here, i.e. the degree must be even. All right. That's all there is to it. I got my papers all messed up here. It's fine. All right. The degree of everything must be even. Okay. This is what it takes to have an Euler circuit. All right. Now, slight variation. I said it's kind of important to understand this a little bit, just because if you understand why it's true, this will allow you to handle slight variations of the basic situation that we're talking about. I would like to think about, what about a path, not a circuit, that uses every edge once. This is like a Euler circuit, only it does not start and end at the same point. But otherwise, it does the same thing. That is, it covers every edge once with no repeats. All right, a path, not a circuit. This is called, there's a name for that. This is an Euler path. It uses every edge once, but it's not a circuit. It starts and ends at 2 different points. All right, that's called an Euler path. Here's an example. How about this graph? Oh, sorry, not like that. This is the graph I want. This one has an Euler path. Actually, this one does not have an Euler circuit. We could look at the degrees here. The degrees. Can anyone say what's the degree of this one? 2. Yeah, there are 2 edges here. How about this one? 2. Yeah, is this confusing to anybody? Somebody, you might feel like, oh, isn't this just like one edge going through it? No, it counts as 2 edges. touching this vertex. There's that edge and that edge. Anyway, this is 2. This is 2. Are they all 2? This is 2. Yeah, there's a 3 here, and a 3 here, and a 2 here, and a 2 here, and a 2 here. All right, those are all the degrees. Now, here, there is no Euler circuit because they're not all even. That's the rule for Euler circuits, is they have to all be even. So these are not all even. So no Euler circuit, all right? But I'm here to tell you there is a Euler path. There's actually a way to cover all the edges without, now it's not going to be a circuit, but you can cover all the edges without repeating any. Check it out. I'll just draw it again over here. If I start here, I can go up, across like that, down here, across the middle, down there, over there, and up there, and finish. Look at that. This is an Euler path. It's not an Euler circuit. It's an Euler path. It's not a circuit because it starts at a different place than it ends, but this is an Euler path. Not an Euler circuit. All right? I would like to think about Euler paths in terms of degrees also. Can we say something about degrees in a graph where there's an Euler path? What I would say is, when I look at the red line, for instance, nearby each point, it looks like an Euler circuit in that it has an arrival and a departure here. An arrival and a departure. Except, at the beginning, there's one extra departure. And at the end, there's one extra arrival. Here, there's 2 arriving paths and only 1 departing. That's because this is where it finishes. You get 1 extra arrival path at the end. And at the beginning, it has 2 departures and 1 arrival. That's because this was the start, which had an extra leaving. So, how would I say this in terms of degrees? I would say they still have to all be even, except where I started is going to have 1 extra edge, and where I finished is going to have 1 extra edge. That means, really, there's 2 odds, and the rest are even. And this is Euler's theorem about paths, is there's an Euler path when there are 2 odds and the rest are even. Those 2 odds will have to be the starting point and the ending point, because the starting point has 1 extra edge going out, and the ending point has 1 extra edge coming in. So this I'm going to write as another theorem about Euler paths this time. A graph has an Euler path, not a circuit, if and only if. This again is easy to check. It's slightly more complicated, I suppose. It says all vertices have even degree except 2 odds. All right? In that case, the graph has an Euler path that's not an Euler circuit. And I will say, parenthetically, although this is important to remember, the 2 odds must be the starting and end points of the path. All right? An Euler path exists when they all have even degree except for 2 odds. And in that case, the 2 odds that you get, they end up being the starting point and the ending point of the Euler path. All right? This is the theorem about Euler paths. So I got well, maybe can I just summarize? So a Euler circuit exists if all even. An Euler path exists if there are 2 odds and the rest even. All right, put this, tattoo that on your arm or something. This is the big thing. It's not that hard to remember. An Euler circuit exists if they're all even, and an Euler path exists if there are 2 odds and the rest are even. All right. Otherwise, there's no Euler nothing, and that certainly can happen sometimes. All right, I got a few examples for you to try. So this will be typical, homework problem or something. I draw a graph. You tell me, does it have a Euler anything? So let's try something like this. How about that? Here's another example. That's Satan's graph. And then,
Wouldn't the star have to be upside down?
oh, is it? All right.
I don't know.
That's
I
just a
don't know.
Yeah, I'm not a.
Yeah, pentagrams are upside down, pentacles are right side.
Okay, sorry. I need to go back to school. How about this one here? All right, that's nobody's graph. So your job each time, tell me, is there an Euler circuit? Is there an Euler path? And I mean, your answer might be no, no, no. But if ever your answer is yes, then try to draw one in. Yes.
For the star one, is each intersection of vertex or just the points?
Yeah, I should say I mean these are all vertices. Everywhere you see an intersection, so all of these are real points here. And same goes for here, of course. All of these questions can be answered by looking at the degrees. Your first order of business should be to decide what are the degrees of each vertex. All right? I'll give you a few moments and then I'll walk around and see how you're doing. Oh, okay. So these are curves. You count. So here's how many total edges are there? There's that. Do you approve this guy? Yes. 5. If you look at it's for other edges. Yeah, yeah. All All right. All right.
But they are all in except two.
Yes. So it has a little path.
Oh, yeah. Sorry, I mean that.
You should draw it in if you can.
I have a question.
Yeah.
When I have to like get a graph and I have to like write it down, the vertices are just like what are existing, and the edges, for example, A, D, A, C, A, B, B, C.
Yep.
There's a little bit of trial and error. You'll figure it out. Kinda gotta go in, you gotta go in a little bit of the zigzag.
Just stop.
No, you can't just follow.
Yes, yeah. You should try and draw the ones. So you started at this 3. This is big. All right. Yeah, so you just said there's no.
Oh, you just say none?
Yeah,
Oh,
and
okay.
you can't draw. All right, let's talk about these. I see some good action going on out there. You got to write down all the degrees, which I suppose it can be easy to mess up from time to time. Hopefully, it comes without too much trouble to find each of the degrees. Now, in this first one here, what I have is 2 odds and the rest are even. That means there is an Euler path. This one right here has an Euler path because I have 2 odds and the rest are evens. Can I draw it in? Maybe I will just, I'm going to draw it bigger down here just so that everybody can see. Can we have a little art lesson here? First of all, when you draw it, it has to start at one of the odds and finish at the other one. And actually, you can do it either way around. And you don't really have to try very hard to make this happen. If you start at one of the odds and draw a path in without repeating any edges, you will naturally finish at the other one. But here's my answer to this. When you're drawing this, yours will probably go different because I'm just making this up as I go along, really. You will probably make different choices than I do, which is fine. I'm going to go down first. You can go wherever you want. You just cannot repeat any edges. So maybe I'll go back across here, up there, down there, up there. How about back here? Like so. And I think that'll do it. All right? There we are. This is how I did it. I covered every edge without repeating any. I hope that you did something similar to that. Can we have a little drawing lesson here? This is something that, for some reason, a lot of people don't believe me when I say this. It is kind of important how you draw the line because it has to be drawn in a way which makes sense to me when I'm reading your answer. All right? This one right here, I like this one. This is a good drawing, in my opinion. Here's an example of a bad drawing, in my opinion. Now, some of you maybe don't like my somewhat sloppy, curvy lines here. And sometimes I see people, they're like, how about I just draw arrows? Like, first I go down there, then over there, then over there, then over there, then 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 there. All right? This, my friends, is a bad drawing. Don't draw it this way because you think that looks better than that. I mean, in a certain sense, I do agree that this looks nicer. It doesn't have this sort of herky-jerky, sloppy line on it. What's wrong with this is really, first of all, there's no indication of where the path starts here. I can't tell where it's supposed to start. But even if you somehow said, like, here's my starting point, here's my ending point, okay, if this is your starting point, where does it go first? Does it go down or up? The answer is you can't tell by looking at the picture. Maybe you know deep down inside your heart, but it's not good enough when you're drawing your picture, all right? Your picture has to be legible to me after the fact. The nice way to make that legible is when you draw it, your line, don't make the line go through the vertices. Miss the vertex a little bit. Because even if you draw the line not following the edges, so this one here is bad. It's a bad drawing. I mean, maybe you had the right idea in your head, but I have no way of knowing when I'm reading your picture. When you're drawing the lines, miss the edges and also miss the vertices. Actually, you might feel like this is better. And I would say, yeah, this is a little bit better. But still, you have a problem if you drive through the vertices. I still can't tell after the fact, sort of, once you got here, which way did you go next? Did you go that way or did you go up? It's not clear if you draw through the vertices. So my drawing lesson is make your line next to the edges and don't go straight through the vertices. All right, you might feel like your picture looks nicer than mine, less sloppy, but it's not. Mine is intentionally sloppy. I'm not saying that I could make it look beautiful if I wanted to, but I am saying I'm making it intentionally look sloppy for the sake of clarity. It's easy to tell where my line is going. If you draw it this way, I cannot give you credit for that. I'll give you something maybe, but it's not worth a check mark, certainly. All right, here ends the drawing lesson. I hope that everybody understands what I'm saying here. I'm not trying to be picky about your drawing, of course. It's just got to make sense to me when I see it after the fact. All right, anyway, the first one here has an Euler path. That was this one. What about this one here? When you look at the degrees, you should have decided that they were all evens, and this means it does have an Euler circuit. Maybe I'll try to draw that one in. Again, you should not have to try really hard to make this work. Probably you can just make it up as you go, and everything will work out fine. When it's an Euler circuit, it doesn't matter where you start, because you're going to end up ending at the same place that you start. If it's an Euler path, you must start at one of the odds and end at another odd. But if it's a circuit, you can start and end wherever you like, and everything's going to work out fine. I'll start at the top here. Maybe I will, just for fun, I'll go around the outside edge first. And then I'll just draw the star thing in the middle, like when I was a kid, like my daddy taught me. Right? This will do it. I mean, there are many other ways that you can make this work, but this is certainly one way that's going to work. Here you go. That's my Euler circuit, and I hope that this is a legible picture. You can tell where I'm going from one edge to the next. Any thoughts about that one? I hope you drew something like this. As I said, there are many, many ways you could have made the path go, and you don't have to feel like you should have done it the same way that I did. All right. Great. And then the last one was this one here. I think we can just leave it at this. So looking at the degrees, I see a 3 up top, a 2 here. This guy's a 5. This is a 4. This is a 5. This is a 2. This is a 3, a 5, and a 3. All right. Are they all evens? No, there are many odds. Are there 2 odds and the rest evens? No, there are many odds. So my conclusion here is there is no Euler nothing. No Euler circuit, no Euler path. And then you have nothing to draw because there isn't anything. So this one right here has no Euler circuit or path. All right. And that means if you really want to cover every edge, you're going to have to repeat some. Yeah?
I have a question for specifically Euler circuits. If you start at a certain vertex, and because the whole point is supposed to end at that certain vertex, can you go over that vertex again if
Yeah.
you get all the edges, or do you have to only go over it twice?
No, you probably will have to go over it more than once. Like I did here, actually. I visited this vertex again here, even though I wasn't done yet. Yeah, I mean, there are 4 edges here, so you definitely have to visit that vertex more than once to cover all the edges. Yeah. All right, that was this one here. No Euler circuit or path. And in that case, of course, there's nothing to draw in, because there's nothing. You can't. All right. Any thoughts about that? I have a cute little handout here, which is going to probably take me longer to hand out than it is to discuss. Cute little handout. Hope you're ready for a cute little handout. This will only take a moment, but they're sort of big pictures that I didn't want to draw on their own. So what we have up top there is I gotta find this. I think it's there. It is. So the one up top is a standard PacMan board. I hope you are familiar with PacMan. Come on. PacMan, the original video game mascot. Before we had Mario's, we had PacMan, and we loved him. PacMan is this guy here. And the goal of PacMan, of course, the question, do you need another one?
Yeah.
Oh, sorry. I'm talking about the PacMans here. It's getting good. Your goal as Pac-Man is to you got to run around here and eat all the white dots, which are black dots on your version of this. The natural question, if you've ever played Pac-Man, you may find yourself wondering: is it possible for Pac-Man to run around and eat all the dots without ever revisiting a location he's ever been to? Is there somehow like one sort of best way that you could do it by running around and never going back to some place where you've been already? Is that possible? If you think about it, this actually is somehow related to Euler circuits and Euler paths, right? If you think of all the possible places where Pac-Man could walk, that makes a graph, doesn't it? Like I could draw the graph in, and you can, if you scribble on top of your handout, you will see what I mean. Like these are the only places where Pac-Man can go, right? And these little sort of, alleys or corridors or whatever make the structure of a graph. Whoa. And if I'm asking you, can Pac-Man go all around this whole thing, cover everything, but never retrace his steps? That's really the same as asking you about, is there an Euler path or an Euler circuit? I suppose if you want Pac-Man to end up where he started, that would be a circuit. That's not really important in the Pac-Man game. Now you have, actually there's these weird two things here which are a little disappointing. But anyway, the question, can I eat up everything without revisiting where I've been, is the same really as, is there an Euler path in there? Along this graph that I made by drawing these red lines in there. And what do you say, yes or no? No. It comes down to what are the degrees in that graph, and are they all evens? And the answer is definitely not. Like this right here, that's a 3. That's a 3. That's a 3. There are many three-way intersections in this structure here, the maze, as they used to call it. And I think actually this was intentionally done by the game designers. They made a lot of three-way intersections, which makes it so that there is no Euler circuit or Euler path. And this makes it so that when you're running around, you must retrace your steps sometimes. And I think that makes it a more interesting game rather than, the alternative would be, if you never had to retrace your steps, you would just like memorize one route to always go the same way. And that's not an interesting puzzle. It's not much of a puzzle, but it's more interesting as a game. So the answer here, is there an Euler path? No. That means when you're playing PacMan, you have to go back across some spots that you've already visited if you want to finish the level. It's a true fact. It's not because you don't know how to do it right. You really do have to revisit some spots you already went to. All right. What about this other thing? Oh, this is just a picture of the lines on a basketball court. I don't know if you ever wondered. I assume the guy with the line painting machine wonders this from time to time. Can you paint all the lines without ever walking back across the same spot that you already been to? It's the same question. And if you know what to look for, the answer is easy. What do you say? Can you paint all the lines without retracing your steps? The answer is no. That's because if you look at this as a graph, you can look at the degrees of the various intersections. Like this one here is a degree 4. This one here is a degree 4. Come on now. But maybe all the others are odds. Like there's many, many degree 3s. This is probably not done intentionally by the NBA or whoever decided where the lines go. But this means because there are many odds, that means there is no Euler path or circuit. So there's many odd degrees here. So no Euler path or circuit. And what that means, practically speaking, is if you're painting the lines here, you have to retrace. You have to go back across somewhere you already did the lines. You can't just draw the entire line like in one big continuous stripe and look awesome to the cheering crowd. All right, many odd degrees, no Euler path or circuit, so you can't draw all the lines in one big loop. All right, it cannot be done. It's very easy to tell if this is or is not possible. That's the using Euler's theorems about the degrees. All right. Any thoughts about that? That was my cute handout. We got about 10 minutes left. That is long enough to talk about one more interesting discovery that Euler made, and it's vaguely related to all this, but I will remind you, if there are all evens, maybe I can write it, I'm going to write this a little differently. If there's all evens, then there's an Euler circuit. Can I say it this way instead? If the number of odds is 0, then this means there is an Euler circuit. No odds means there's an Euler circuit. If the number of odds is 2 odds and the rest even, this means there's an Euler path. And if the number of odds is more than 2, this means there's none, right? No Euler circuit, no Euler path. This is what we've talked about so far. If the number of odds is 0, then there's an Euler circuit. If there's 2, there's an Euler path. And if there's any more than 2, then there's none. There's one situation which is unaddressed here in terms of the number of odds. If you look over here, you will see. If there's 0 odds or 2 or more than 2, what about if there's 1 odd? I never said anything about that. What about a graph which has 1 vertex with odd degree and the rest are even? So what if one vertex is odd, the rest even? This is also something that Euler himself thought about. What if one vertex is odd and the rest are even? Can anybody give me an example of a graph that's like that? Or maybe something like, okay, here they're all even. If I add something like that, Now I got two odds. Can you make it so that there's only one odd? Yeah.
The line, you put this away. You put the line away.
Take away
The in the middle one.
this one?
No,
The
one.
diagonal I just did?
Yeah.
Okay.
And then it's just 2, and then you put on one of the vertices just a random line.
Oh, okay. So this is now 3, that's 2, and that's 1.
So does there have to be a vertex?
Yeah, you can't have an edge with no vertex on the end. Yeah. Anyone see how to do this?
Can you put like a half line, like in the middle?
A half line.
Oh,
No.
Still be a 1.
Oh, you mean just like this?
Yeah.
Yeah, now this is a 1. That's now a 4. This is my, yeah? It's not possible, she says. Yeah, it's not possible. This is the other thing that Euler discovered. What if one vertex is odd and the rest are even? This is impossible, actually. This cannot happen. And this one also, there's once you look at it properly, it's not so hard to see why this cannot happen. This is called. I'm going to write this as another theorem. This one really does have a standard name. This is called Euler's sum of degrees theorem. Euler's sum of degrees theorem. Sum meaning add them all together. The sum of degrees theorem. And it says, this is another thing that Euler discovered. Is this true of any graph? In any graph, the sum of the degrees equals 2 times the number of edges. If you add all the degrees in the whole graph, what you get is 2 times the number of edges. And this is actually, I mean, maybe it sounds complicated the way I say it, but this is not hard at all to see why this is the case. It's the case because every edge has 2 ends on it. And so if you're adding up all the degrees, you're counting up all the number of times that an edge touches a vertex. Since every edge has 2 ends, then 2 times the number of edges would add up to the total number of times that any edge hits any vertex, and that would be the sum of all the degrees. So in any graph, the sum of the degrees equals 2 times the number of edges. Can we just check that? For this example right here, the sum of the degrees would be 2 plus 4 plus 1 plus 1 plus 2 plus 2. I'm just adding all the numbers that I see on the picture. That is 6, 7, 8, 9, 10, 11, 12. And the number of edges is 6, isn't it? I got 1, 2, 3, 4, 5, 6. So there are 6 edges. And the sum of the degrees is 12. This will always work out. One thing that you can say very easily about this is the sum of the degrees equals 2 times the number of edges. This means the sum of degrees is always even, because it equals 2 times something, all right? And that means there cannot be only one. You can't have one odd and the rest be even, because then if you added them all together, then the total would be odd, and that's not allowed. The sum of degrees is always even. So we can't have one odd and the rest even. Because in that case, if you were to add them all together, you would end up with an odd, and that is not allowed. The sum of the degrees must be even, all right? I have, in our remaining 4 minutes, I have a fascinating true story about the sum of degrees theorem. The sum of degrees theorem once played an important role in the NFL. Can you believe it? I believe this is a true story, although I've tried to look up the precise details and I haven't been able to find like what year in particular this came up in. But the sum of degrees theorem actually came up in a weird way. This is a weird NFL story, I guess. This is about, I am a person who doesn't really know or care anything about the NFL, but This is about when they were making the schedule for the NFL in one year. At this point, I guess the NFL is divided into two conferences. Anybody know anything about this? There's the AFC and the NFC. I think I'm right about this. And mostly people play games inside their own conference. So once upon a time in the NFL, they were making the schedule for the year. They have to decide the schedule. And they decided that each team is going to play. Oh, let me just say, at this point, there were 13 teams. I think there are more than this now, but 13 teams in the AFC, which is one of the conferences. And they decided that this year we should play 11 games each. So each team is going to play 11 games with the other teams in the AFC. So we have 13 total teams, and they said each team is going to play 11 games total. And so they decided this, and then they gave this to somebody and said, okay, make us up a schedule where each team plays 11 games total. This is the scenario, all right? It sounds like this is a reasonable request, but actually this is mathematically impossible because of the sum of degrees theorem. The moral of the story is, in graph theory and sometimes in real life, you can't just do whatever you want. Because this situation, this description here, would create a graph which is impossible. If you think about the way this would look, in a graph, it would look like each team is a vertex and each team is connected up to all of the other teams that they are playing a game against. All right? And according to the rules here, it should be 11 other teams that each vertex is playing a game against. Is that 11 there? I mean to make this 11 edges. So each team is a vertex. There are 13 vertices, and each of degree 11, right? Because each team is going to play 11 games. What is the total sum of the degrees in this graph? It would be whatever 13 times 11 is, because if I add up all the degrees, it's 11 plus 11 plus 11, 13 times. But that, I did this ahead of time. The total sum of degrees is, it would be 13 times 11, which is 143. That's odd, and so this whole scenario is mathematically impossible. You cannot just make up things like this. Schedules, this happens with schedules. I'm sure people at Fairfield University know facts about this. If you're making any kind of, designing any kind of thing about teams playing each other, or like your grandma sitting next to your cousins at a wedding or something like that, there are like basic mathematical restrictions in play, and you cannot just do whatever you want. That's the moral of the sum of degrees theorem. So this is impossible. That's what I'm saying. All right, graph theory. It really matters sometimes.